Welcome everyone to this treasure hunt. I hope all of you are ready to help this pirate ship to find the imaging modality. The instruction to achieve this is that you must follow the clues that are marked with numbers on this map. And if you do it correctly, you will be able to discover what is the imaging modality that is hidden in the treasure chest. Good luck! Let's begin with the first clue, description. Obtaining anatomical images represents a challenge to achieve that good quality images are produced without damaging the patient in the process. That is why imaging modality is a non-invasive imaging study that uses light waves to obtain cross-sectional images. As it is a non-invasive and a non-contact technology, it is particularly attractive for ophthalmological application, and it is good as a glaucoma and retinal diseases treatment guidance. Also, with this modality, it can be seen the retinal layers in a monitor.
Now we are gonna go to the second clue. So, how does it work? Actually, this imaging technique is pretty similar to the one that almost all of us know, the echography, or also known as ultrasound. But the main difference between them is that the first one works using sound waves, and this one works using light waves. This can be very effective to improve quality. The functional principle of this technique is light interference, therefore a light interference setup is needed. Right now, we are seeing a schematic diagram of the basic setup. The system works with light from a low current source that is split into two paths by a coupler, also known as a beam splitter, and the source is directed to two different arms of an interferometer. One arm is the reference arm and the other is the sample arm. The light is shaped by various optical components like mirrors and lenses. The different structures are going to have different indexes of refraction, and light will be scattered when encountering an interference. The resourcing light from both arms will recombine and the coupler generate a pattern, which is recorded, and that's how the image is constructed. It is important to know that the penetration and the depth will be determined by the wavelength and the source powered, and that the most common source of light are the edge-emitting diodes. The temporal coherence determines the depth of the resolution. The light is split into two paths and they may or may not be the same length. If they are, they will recombine and cause an interference, so the resulting light intensity is higher. If not, it will decrease. This is the way that the light echoes detection can be described.
Now let's go for the advantages and disadvantages. Let's get first into the advantages. The first one and most important is that it is a non-invasive method. It also provides a faster and easier method for diagnosis. It gives results quicker as compared to other traditional medical diagnosing procedures. It is also a computerized procedure, and therefore chances of error are reduced. It gives a better image of the test results. This process follows a higher number of scans and thus provides an image of higher resolution as a result of the diagnosis. It also involves rapid data acquisition, which is about 2.4 seconds. The device used in this procedure is portable. It is compact and therefore makes it easy to carry. Modern versions of the device used in this procedure are easy to use, and therefore the personnel don't need long training. Now let's get back for the disadvantages. The first one is that it has a limited penetration power. It can result in a penetration up to 2 to 3 millimeters, ideally being it 4 millimeters. The femtosecond laser used in this procedure is expensive, and therefore it would not be available in smaller clinics. Finally, since it depends on light waves, it is not suitable for use in patients with cataracts.
Now we're going to talk about applications. At present moment, the optical coherence tomography imaging is used extensively for imaging the macula, the optic nerve, and the retinal nerve fiber layer. And It aids in analyzing the morphology and quantifying changes in various diseases states. For example, the automated retinal thickness measurements generated by the SDOCT systems are used clinically for the monitoring progression of diseases such as wet age-related macular degeneration, or abbreviated AMD, and macular edema from various causes including diabetes and retinal vein occlusion. The ability to detect fluid within the retina and the thickness alterations induced by this fluid helps direct clinical decisions regarding treatment. The diagnosis of macular hole and its differentiations between lamellar holes and pseudomacular holes have become straightforward using OCT. In addition, the size and configuration of macular holes become determined by OCT correlates well with the functional and anatomic outcomes following surgical intervention. Evaluation of the vitreoretinal interface using OCT is important and in the evaluation and treatment of diseases of the vitreomacular interface such as epiretinal membranes and vitreomacular traction. In addition, optic disc morphology and retinal nerve fiber layer thickness measurements using OCT monitor the progression and helps quantitatively assess the treatment response in patients with glaucoma.
Now, let's see what is in the treasure. Congratulations! The imaging modality is optical coherence tomography. We hope you learned something about this and enjoy following the clues.